All right, welcome to this walkthrough of our classification of matter activity that we did in lecture yesterday. And the purpose of this video, I just wanted to kind of give you a way to look at the whole process here and get a little bit more detailed of an explanation for why things were happening and why I wrote down some of the answers that I did. And so before we actually get to the questions, I really want to take a chance and look at these different pictures and try to get some ideas for what the pictures are saying and kind of how to see the differences between them. So, if we look at this, the model here, it says matter is defined as anything that has mass and takes up space. An atom is the smallest particle of matter that can involve itself in a chemical reaction. And again, we're going to skip that part about nuclear. We'll come back to that in a couple of weeks. All matter is composed of atoms. Matter can be classified as one of the following: either an element, a compound, a homogeneous mixture, sometimes referred to as a solution, or a heterogeneous mixture. And here are some examples of each of these. So in this first picture, we have an element, sodium. And so one thing that we want to kind of look at and focus on here is that this is an example of a metal sample. And we can see that in this metal sample, we've got a whole bunch of atoms. They're very, very close together. This is exactly the kind of thing that we were talking about when we were describing the solid phase yesterday. We've got all of these atoms all together. They're all lined up in a very ordered kind of fashion. That's what gives solids their rigidity and their inability to transform into different shapes or take on different volumes. So we can see that really there's a whole lot here, but none of the atoms are actually connected to each other in any kind of significant way. And if we compare that to figure 2 here, where we also have an element, this is a non-metal element. In this case, it's chlorine. We can see, okay, chlorine, each one of these circles, each one of these balls represents an atom of chlorine. And we can see that each molecule of chlorine has 2 of those atoms held together with each other. And we would call that thing that holds them together a chemical bond. And so when we look at chlorine, we can see that chlorine doesn't exist as individual atoms the way that sodium did. It exists in these molecules, these small paired up arrangements of 2 chlorine atoms that are bonded together. And that's one of the things that makes metals and nonmetals different from each other. And the other thing that we should notice here is look at the spacing. See how close all of these were. See how far apart some of these atoms are from each other. None of them are touching, with maybe a couple of exceptions. And this makes sense. Chlorine usually exists in the gas phase. And we know that in gases, those molecules are really far apart from each other, which allows the gas to expand to whatever size container it's in and take on the shape of whatever container we put it into as well. And then in this third picture, we're looking at, here are molecules also. We can see that there are molecules here of different kinds. So I've got a molecule of chlorine here, or excuse me, an atom of chlorine here, but I've got an atom of hydrogen here. Now they're held together in the same kind of way that these nonmetals are in this elemental molecular sample. So we would call these molecules as well. just like we call these molecules. The only difference between these molecules over here and these over here is a compositional difference. In the sample in figure 2, these are elemental samples. These are elemental molecules. Every single atom in this sample is exactly the same. They're all chlorine. In this sample, we've got molecules as well. The only difference is that every single molecule isn't composed of just chlorine, but we have hydrogen and chlorine. But we also notice that every single one of these molecules looks exactly the same. They have the same composition regardless. One hydrogen bonded to one chlorine. And that's an important thing to note there as well, because that's one of the things that's going to set a compound apart from a mixture. Because it's really easy to get those two things confused, because you look at, okay, I get elements. Elements all have the same kind of atom. So if I see a sample that only has one kind of atom in it, I know it's an element. But telling the difference between a compound and a mixture can be kind of difficult sometimes, because we see that there are different atoms present in both. How do I tell them apart? Well, one of them is compositionally. Compositionally, I can see every single molecule in this sample is the same. They're all HCl. They all have one hydrogen and one chlorine. And if I were to change that composition, I would no longer be talking about the same substance. If I had two hydrogens and one chlorine, it's no longer the same substance. It's a different substance. In figure 4 here, we're getting a look at what is called an ionic compound. And this ionic compound, NaCl, has some of the same characteristics. I can clearly see I've got one sodium and one chloride in this kind of ratio. The difference is, notice here, we don't really have molecules here. We have kind of sort of similar to what we saw in the metal sample, where we've got this arrangement of these atoms that are kind of associated with each other, but not really chemically bonded to each other. We kind of got the same thing here. Now, technically speaking, we consider these to be chemically bonded. They're bonded through something called ionic bonding. That is one difference between ionic compounds and elements, in that there is an actual attraction from one ion to the other because of the difference in charge. But I can see here what makes this a compound is that there is a very set formula that goes into it. One sodium, one chloride. One sodium, one chloride. The ratio is the same. There's a uniformity in that compound itself. As opposed to figure 5 here. Figure 5 here, we've got what are called homogeneous mixtures. So we know a homogeneous mixture as a mixture that has a uniform appearance. So this is another place where we can get confused between compounds and mixtures, because from a standpoint of appearance, they look really similar. So how do I tell them apart? What can I do? Well, if it's a mixture, I should be able to separate it in some kind of way. So in the case of a solution of sodium chloride, I've got water, and I've got sodium chloride, the salt. There's got to be a way I can get the water and the sodium chloride apart from each other. And we know what that is. We could boil off the water. And if we boil off the water, the salt gets left behind. That would let us know that we've got a mixture there. But the other thing that's important is we can see that there is a difference here in terms of the composition as well. Yes, each one of these solutions has sodium ions, chloride ions, and water in them. But there is a considerable difference in the amount of water in each. In this panel on the left, there are more water molecules. In this panel on the right, there are fewer water molecules. And yet both are considered to be solutions. And both are considered to be homogeneous solutions of sodium chloride. So one of the things that sets apart a mixture is this variability in composition. I don't need to have this exact ratio of one thing to another to be a mixture. I can have a more variety of components. And then finally, figure 6, this is an example of a heterogeneous mixture. In a heterogeneous mixture, what we see in that is that we can clearly see that there are two substances present. There is the water, there is the silver chloride. The difference between this and these is that the mixing isn't there. This is very easy to see. Okay, water is here, the solid here in the bottom is there. We could separate out, again, physically, but the process we're looking at there would be more like filtration as opposed to boiling. And so we can kind of summarize this with figure 7 here. We're going to actually make a flow chart similar to this in lecture on tomorrow. But it kind of summarizes the whole thing. How do I know the difference between a pure substance and a mixture? It comes down to how it's made. In a mixture, I have multiple substances present, and they can exist in any ratio. They can exist in any kind of combination. Whereas pure substances, they have a fixed composition. And so if I deviate from that composition, I change the entire identity of the substance. What's interesting about this as well is actually, if I have physical processes, I can take the mixtures and convert them into pure substances. So, take example again, that salt water. If I go through the physical change of boiling off the water, I would be left with two pure substances at the end. The water that I separated, which has a fixed ratio, 2 hydrogens to 1 oxygen, and the salt, sodium chloride, which has a fixed ratio of 1 sodium to 1 chlorine. If you drill down from here, what we'll see is that pure substances are pure. They have a fixed composition, and we cannot physically separate them. So I can't take the water that I have and turn it into hydrogen and oxygen just by simply separating them. I'd have to do some kind of a chemical process to get the hydrogen and the oxygen to separate from each other. And that gets into kind of the fundamental difference between elements and compounds. Elements and compounds, in elements, we see that we only have the one type of atom. In compounds, we have more than one type of atom. And if I wanted to turn an element into a compound or a compound into an element, I'd have to go through some kind of a chemical reaction to do so. The difference between homogeneous and heterogeneous is how you can view them. Is it easy to distinguish one part of it from the other? So in a homogeneous mixture, you really can't tell how many components are in there. In a heterogeneous mixture, you can. And so when we go through the key questions now, Now we can kind of look at each of those and see the differences. So the first one says, how do I distinguish between the four different things here? Well, if I'm looking at an element, first thing I should notice is that all of the atoms are the same kind. And again, that puts us back up here to figures 1 and 2. This sample, all of the elements are the same kind. Here, all of the elements are the same kind. The only difference between them is really the difference between metals and non-metals in terms of how they're arranged with each other, either in the solid phase and they're all kind of bunched together, or in the liquid and gas phase where they're a little bit more separated. And we tend to see with non-metals bonding occurring as they make molecules instead of just atoms. With a compound, we have different atoms present, but they're always in the same proportion. And so if I'm looking at a compound sample, I'm only going to see one substance present. That substance is going to have some kind of either a molecular or ionic kind of view, but it's going to definitely be one substance. It's going to be every single particle of that substance looks the same, whether they're all HCl's, whether they're all carbon dioxide, CO2, whether they're all sodium chlorides, NaCl's. They're going to have that uniformity in their composition that I'm not going to be able to tell the difference between one and the other. Mixtures, on the other hand, I have to have two or more substances present. And the combination there is physical instead of chemical. In compounds, they're a chemical combination. That's what leads to that fixed ratio, that unique proportion. But in a physical combination, in a mixture, doesn't have to be. You know, if I make a salad, I can make a salad in a number of different ways, throw in different amounts of lettuce, different kinds of lettuce, throw in carrots, throw in tomatoes, throw in whatever, and use different amounts for each one, and they'd still come out as a salad. But for a compound, if I change the ratio of water from H2O, it's no longer water. And so that kind of leads us back to pure substances. In pure substances, you're only going to see one kind of substance present. It's either going to be an elemental substance where all of the atoms look the same, or it's going to be a compound substance where we've got a very fixed ratio of one element to the other in these compound units, either molecules or kind of these ionic units. With question number 2 here, we kind of talked about all the differences between figures 1 and 2, looking at sodium versus chlorine. The thing that we know that is the same, all of the atoms in the sample are the same kind of atom. So we don't have to look at anything kind of else other than that. But what's different is just a compositional thing. Metals tend to be solids. They tend to be arranged very, very closely. All the atoms are associated with each other, but they're not really connected to each other by what we would call, formal bonds. Whereas nonmetals tend to have those bonds in them. They tend to be more molecular, and depending upon the phase of matter, because the nonmetals do exist in the solid, liquid, and gas phases. They tend to be more individual substances in that molecular gathering. They tend to be a little bit more separated, a little bit easier to separate. Even the ones that are solids, very easy to melt, very easy to boil, doesn't require a whole lot of temperature to do so. Number 3 was the question that most of us had problems with yesterday. Let's talk about just real brief here. Molecules of sodium chloride, no. The thing that makes a molecule is that we have to have it as kind of a unique unit. It has to be something that we can separate out from the others. And so if I look at that picture of sodium chloride, I can see that, yes, there is definitely a repetition in there. There is a repeating unit, but we wouldn't call that a molecule. I can't look at this and say, oh, here's my molecule of sodium chloride. Because you would look at this same chloride ion and say, well, why isn't it this one? Or why isn't it this one? So what we tend to talk about in ionic compounds, there's another term that we used here. It's called a formula unit. We're not going to use that term often, but a formula unit is kind of the more formal way that we describe that repeating unit inside of an ionic compound, as opposed to a molecule. Because again, with molecules, there's some level of separation. We can look at each of these and say, okay, here's that repeating unit, and that repeating unit isn't in doubt. There is no question about, oh, well, what if this hydrogen was actually bonded to this chlorine? It's not. It's only bonded to this one. And so that makes it a little bit, that's one of the kind of the differences that exist between those. We look at question 4. What are the differences between a homogeneous mixture and a heterogeneous mixture? Give an example of each. Well, that's what we kind of talked about. It's the appearance. It's how it looks. If I look at a mixture and I can't tell all the components that are in it, it's homogeneous because it looks the same throughout. The example given was salt water. We could easily do this for sugar water. We could easily do this for certain metal alloys like steel, stainless steel, brass. There's a number of things out there in your lecture notes about that. Heterogeneous mixtures, on the other hand, they lack that uniformity. So salad is a good example of that. Things like concrete. If you take a sample of sidewalk and you smack it, and you can look and you see all the different types of stones in there. You can see some of the sand that was put into it. You could separate all of that out pretty easily if you wanted to. Exercise 5, can the relative amounts of components vary in a mixture? Absolutely. This is where figure 5 comes in, where we can look at those 2 samples of sodium chloride, water, and see that the one has more water in it and the one has less water in it. They're both still salt water. Another classic example around here, tea. If you make sweet tea, you can make it with a lot of sugar, you can make it with a little bit of sugar. Everybody's version of sweet tea is different, but they're all going to call it the same thing. It's sweet tea. It's tea, water, sugar. But what comes of that, how you make it beyond that, what the recipe actually is, it's going to vary from person to person. So the recipe changes in mixtures, changes all the time. But that recipe can't change if it's a compound. So that's question number 6. Compounds have to have a uniform composition. Otherwise, they would be different substances. So easy example of this, water, we all know. Formula is H2O. Change that water just slightly, turn it into H2O2, different substance completely. One is very safe, easy to drink, has virtually no reactive kind of properties other than just some real basic, simple ones that exist with very, very reactive kinds of metals. Hydrogen peroxide is an oxidizer. It's not the strongest oxidizer out there, especially if you have the, kind of the drugstore version of hydrogen peroxide, but it's reactive. It's reactive enough that you have to store it in a brown bottle or it will just decompose in the sun. So different compounds have different kinds of chemical and physical properties with them. And because of that, we have to look at that that's what makes a compound a compound. That's why we have to know what the ratio is and how to deal with it. All right, question 7. Tap water will leave white deposits when it evaporates. Is it a mixture or a compound? Well, if it was a compound, if it was just water, when the water evaporated, there'd be nothing left in the cup because it would be the only substance. So the fact that we have a white substance being left over indicates that there are two substances present, or at least two substances present. And if there are multiple substances present, has to be a mixture. Has to be a mixture. Now, in this case, it's a homogeneous mixture because, well, you couldn't tell that there was anything dissolved in the water prior, but it would definitely be a mixture. These two are two true statements, and they're just kind of going after our thinking here. So the smallest particles unique to an element could be atoms or molecules, and we saw that. That's a metal versus non-metal kind of thing. The smallest particles unique to a compound can't be atoms. That's also true, because remember, atoms are a single element. And if I have a compound, I don't have a single element. I have at least two elements that are present and in a fixed proportion. So what we'll see with compounds is that instead of breaking down to the smallest particle being an atom, they're going to break down to the smallest particle either being a molecule, if it's bonded together with those bonds like we saw in pictures, or it's going to be like an ionic unit, like an ionic crystal, like we saw with the sodium chloride or the silver chloride. All right, last questions here. So you find some seawater on the beach. You see in your little sample that there are some grains of sand in there as well. You filter the mixture. You put the sand in vial A. You take half of that liquid and put it into vial B. You heat the other half of the liquid until it boils. You collect the gas that escapes and you cool it down. That gets put into vial C. And there's some solid left over in the pot. That's put into vial D. So if I look at this kind of from the start, the original sample has to be heterogeneous. And the reason it's heterogeneous is you've got all the stuff that's involved with the water, plus you have the sand. And so those are two substances that we know of. So we know it's a mixture. And the fact that it's easily seen that we know that we have two substances means that it has to be heterogeneous. Because if I couldn't see the sand, I would know that it would be homogeneous, because I'd be, okay, I just got a cup of water here. But I don't. I have solid and liquid in the same sample. So I know I've got multiple substances present. I can easily see that one is different from the other. That's heterogeneous. Now, once we've separated the sand out of there, now we have just a liquid. So the sand is in vial A. We're told that that solid is pure quartz. Well, quartz is not an element. It's not on the periodic table. It's a combination of elements. It's usually silica, silicon dioxide, SiO2. So that's a pure compound. We're told that it's pure, so we don't have to worry about it being called a mixture. We also know that it's made out of more than one compound, or more than one element, because quartz isn't an element. So that makes it a compound. The liquid itself that we drew off here, well, we don't know at the time until we do the remaining things that this is a mixture as well. It's homogeneous because, and that was one of the reasons why we would be confused, at least initially, because we couldn't see that there was anything in it other than it just looks like water. But once we boiled it and saw that it separated, that would let us know that it was a mixture. So a homogeneous mixture would have been that seawater sample. The liquid that reforms in C, pretty safe to assume that that's just the water. And so that'd be a pure compound of H2O. And the solid that remained, that was after the boiling, we could be pretty confident that was a pure compound, in that it was salt, sodium chloride. In question 14, we're asked to identify things as being pure, homogeneous, or heterogeneous. All right, these are kind of tough ones. We're starting to get into some natural products here. Now, natural products, things that come from nature, generally tend not to be pure substances. They usually are, a mixture of quite a few things. At the very least, white grape juice. We know that there is water in grape juice. We also know that it's sweet. There's sugar in it. There we go. We've got two substances. So we know it can't be a pure substance. What else is there? Well, now it comes down to uniformity. How does it look? White grape juice, it all looks the same. Clear, uniform color. Have no way of knowing that there was different stuff in it unless I tried to boil it off. Homogeneous. An open bottle of beer, this one's going to be heterogeneous. And the key word there is open. If this was a closed bottle, we would put it into the homogeneous category because we've got water and we've got, all the other ingredients that come into different kinds of beer. But because it's been opened, as soon as we open anything that is carbonated, you're going to get bubbles. Those bubbles are going to be easily seen, and that's what's going to make it heterogeneous. Because now, not only do you have the water and the barley and the hops and whatever else goes into your beer, but now you have those carbon dioxide bubbles that are being released, and you can very clearly see the carbon dioxide bubbles inside of the beer. So it makes the beer foamy. C, water with ice cubes. This one's pretty easy. This one's heterogeneous. And the reason it's heterogeneous, I can clearly see, even though I have two pure substances here, water and frozen water, the fact that they are together, I've got two substances present. And I can very clearly see the solid versus the liquid. It's heterogeneous. The last one, a fresh garden salad, heterogeneous as well. Very easy to see, okay, I've got my lettuce, I've got my tomatoes, I've got my cucumbers, I've got my carrots, I've got my radishes. They're all there. They're all mixed together. They're all very easily separated as well. Last question. If you have a container with hydrogen gas and oxygen gas in it, do you have water? The answer is no. Hydrogen and oxygen are the components of water, but until those two gases actually react chemically, they will remain just a mixture of hydrogen and oxygen. You've got to do something to get them to react with each other. If you don't get them to react with each other, they will remain just hydrogen and oxygen. Water comes about only as a chemical reaction. So that goes back to, if you go to that flow chart on page 3, how do you turn elements into a compound? It has to go through a chemical change. Simply mixing them is not enough to get them to actually react. You have to spark that reaction in some kind of way. So I hope you found this video helpful. If you have any questions, bring those with you to lecture tomorrow, and we'll talk more about this then. Have a good day.